Alrighty, so this is the second video of Wednesday, so 2.2. And so we just talked about average rates of change. And we've talked about linear functions, right? Like y equals a plus bx. We didn't call it kind of, maybe you've heard of it as y equals mx plus little b. So look at the equation for a line. Now we're going to kind of hone in on what we've just learned about average rate of change to kind of refine our definition of a linear function rather than talking about common difference and stuff like that. So last section we saw functions had different average rates of change in different intervals. Like the tile one, she did 21 in the first little bit and then like 47 over the other 4 hours. So what type of function will we have if the average rate of change is the same on each interval, right? So my rise and run would be the same each and every time, up and up and up. I would get a line just like that. A linear function. I gotta do, apparently it's really thirsty. Am I recording? Okay, good. Right, so, oh, I need my notes. There we go. So a linear function is a function of the form f of x equals mx plus b, because we're using function notation here, but usually we'd say y equals mx plus b, where m and b are real numbers. Remember, we only care about real numbers, okay? And the graph is a line. And I know what you guys might be thinking, like, oh, isn't this a line? That is a curve. So when we talk about lines in math, we're talking straight lines. Anything that is not straight is a curve, okay? More math lingo for you. So, let me write that a little bit better. We're going to talk about different ways that we can draw a line, but it's mostly in this form. Something times x plus just another number. And x is at most to the first power. Okay? So which of the following are linear functions? We look at A. F of x equals 2 plus 3x. I would say this is linear, right? Where b would be 2 and m would be 3. So that one's going to be linear. What about b? Minus 2x plus 1. All I was told about m and b is that they're real numbers. They can be negative numbers. So I would say that b is also linear. And see, x is not squared or not in the denominator at all. Let's look at c. 3x squared plus 1. Do we think that's linear? This one is not linear. If x is raised to any power higher than 1, it's not linear. What about k? I now have a fraction going on. But x is just still in the numerator. It's still raised to the first power. So this could be written as like 1/4 minus 5/4 times x. So this is also linear. Just looked a little different. As long as x is in the numerator and its power is 1, it's a linear function. Okay? And there's only one of them. It's not like x times x, because that would be x squared. Okay? So this is a cool exercise, I think. So the chapter is called Constant Rates of Change. So the average rate of change isn't going to change over the interval, and that's what this example is going to show. So if we're looking at f of x equals 2 plus 3x, find the average rate of change over the following intervals. So between x equals 0 and x equals 1. So our a rock would be f of 1, oopsies, minus f of 0 over 1 minus 0 is going to be 2 plus 3 times 1 minus 2 plus 3 times 0 over 1. So what is that going to be? 5 minus 2 over 1, which is going to be 3. And we're not giving any units, we're just given a function. So 3 is an appropriate answer. Or given units, my answer also has to be units. Ooh. All right, so let's do another interval. So that was just an interval from 0 to 1, right? So going just like one step further from 0 to 1. Now what if I go from 1 to 4? I kind of said this earlier, I don't need to do the average rate of change from 1 to 2, 2 to 3, 3 to 4. I just need to do average rate of change using 1 and 4. So f of 4 minus f of 1 over 4 minus 1 equals 2 plus 3 times 4 minus, the reason I do big parentheses like this is because that minus, you might forget to distribute it over, right? So 2 plus 3 times 1 over 3. 4 minus 1 is 3. So 2 plus, what's 3 times 4? 12. So this is 14 minus 5 over 3, which is going to give me 9 over 3, which again is 3. So no, even though my interval here from 1 to 4 is 3 times as big as from 0 to 1, they still have the average rate of change. Now, what if I do it from C to D? This is kind of confusing, right? Like, I'm not going to plug in any numbers. I'm going to plug in D and C into my function and see what happens. So I'll get 2 plus 3 times C. Oh, sorry, not 3 times C. 3 times D minus 2 plus 3 times C over D minus C. And that's going to be what? 2 plus 3D minus 2 minus 3C. So 2 minus 2. And I'll get 3D minus 3C over D minus C, which is, I can pull out a 3 and then these cancel out, and I'm left with 3. So I didn't even know the difference between C and D, but I can just show right there that I still get 3 out, which is pretty crazy. So what is this? Remember, our function is f of x equals 2 plus 3x. I'm getting 3 each time. So what does this tell us about m and y equals mx plus b? Give you a time to think. M is our slope. Which we also can call the average rate of change in a linear function. Well, it's already in a linear function. There we go. Okay. So we can kind of write it a little nicer. So right, let f be the linear function, f of x equals mx plus b. Then the rate of change of f is the constant m, and the initial value, we also used to call that the y-intercept of f, is the constant b. Okay. So let's do some practice on making linear functions with the problem that we're given now that I know that m is my rate of change and b is my initial value, and then see if we can do some average rate of change with that as well, right? So water is being pumped into a swimming pool at the rate of 5 gallons per minute. If I ever see unit divided by another something, that tells me that that's most likely going to be, that's a rate. Something per something, that's a rate. So that tells me that that might be M, okay? Initially, ooh, that's a really big word. Initially, the pool has 200 gallons of water. Perfect. Great. That already tells me that that's my initial condition. So find the linear function that models the volume of water in the pool at any time. All right, so I just saw that my initial value, sorry, is going to be 200, and the rate is going to be M, which is 5. So I can just put these all together and say 5x plus 200, and we're done. I think that's good, right? Oh, we're not doing anything else with that problem. Okay. That one was fun. Okay, cool. So when looking at a graph, we care about the graph steepness. We talked about this like when we talked about the farmer problem. The largest rate of decline was the steepest negative slope, or how fast it rises and falls. So the slope of a graph is rise over run. So just kind of like average rate of change for linear functions. They all have slope, rise over run, delta y over delta x, f of b minus f of a over b minus a. They're all fun nicknames for the same thing. It's like if each of your different friends had a fun nickname for you. Okay. I hate when people try to give me nicknames. Alrighty, example time. So below is a staircase in a coordinate plane. The red line is the edge of the trim board. Find the equation of the line. So I didn't actually draw the line that I was supposed to draw. Let me draw it now. Something like that, a little bit, right? And it's gonna like hit right here, 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 and here. So, right, if I'm given my function f of x equals mx plus b, 1 second. My God. The best thing to find right now, in my opinion, is b, the initial value, right? That's usually easy. That's when x equals 0. So we go over here and it's 8. So looking at the graph, so b equals 8. What about m? Just pick 2 points and find the slope between them. It doesn't matter which two, because linear functions have constant rates of change. Just like we saw, if I do it from 0 to 1 versus if I do from 1 to 4, it's going to be the same. So it doesn't matter. So to find to find m, find the slope between any 2 points on the line. All right, so I usually like to do like something that has 0 involved. So 0, 8 is a point, and I know that because that's my initial condition. And if I go over when x is 12, y is 16, okay? So I can find my average rate of change, or we can just call that m, is going to be 16 minus 8 over 12 minus 0. which is 8/12, which is 2/3. Yeah, 2/3. So m equals 2/3, and I can put everything together, and I get 2/3 times x. You could also do like 2x/3. That's the same thing. Plus 8, and that's it. And when we write functions, nothing in the function needs any units. I hope that's clear. Just when you give an answer, that's when you interval. So don't write like plus 8 feet. You don't need that. Okay, cool. So now we're asked to graph the function 2 plus x. You're like, Mackenzie, I should use my graphing calculator. No, you could do it on your own. So it's just a line. I always like to do my graphs in blue, like the axes. I don't know why. So that's our axes. We're gonna name them. That's x. This is f of x. Boop, boop. Those are our little ticks. Okay, so when f of x equals 2 plus x, tells me that b is 2 and m is what? M is 1, right? There's nothing in front of x, but so it's not 0, because 0 at times anything would just be 0, wouldn't be there. It's 1, okay? I know I look like I'm crying, but I just really need to sneeze. So my initial condition is 2. So I'm gonna go right here. And then I know I'm gonna increase each time. So, all right, f of 0 would be 2, f of 1 would be 3, and so on. So 3, 4, and I can just connect my lines from there. And same for the negative one, right? Like -1 would be down here, and our line would continue like that. All right. So that's how we can use our initial condition and our slope to easily make a graph. And it's a line. So like I just really need to extend the first 2 points that I used. Okay. So this is one of my favorite problems. I really like this cool problem. So John and Mary are driving westward on I-76. Fun fact, interstates that are even numbers are east to west and odd numbers go north and south. So 77 goes up, 22 goes that way. Below is the graph of their distance from Philadelphia in miles and time in hours. Great, gives me my units right there. So x equals 0 is noon. So 0.5, half an hour after noon would be 12:30, or as I call it, noon 30. All right, so this would be like 1 p.m., 2 p.m., and so on, right? This would be like 12:30, 1:30, right? Because it'd be like half an hour, right? Okay. And there's like a point on each one of them, okay? That's our graph. It's beautiful. So how fast are they traveling? Who is faster and how does this show on the graph? So, oh my God, I didn't say who is who. Who is the maroon one? That's Mary. And John is in orange. John, Jacob. Okay. So let's talk about Mary first, right? All I need to find, we can see clearly that these are both lines. They're straight lines. So they're not curving at all, so their average rate of change isn't going to change. It's just a straight line. So that means that I just need to find 2 points on its graph and find the slope between them. Doesn't matter which two, probably just ones that are easy to calculate. So I usually like to do the initial condition. So at Mary, it looks like she starts in Philadelphia. So she has the point 0, 0, and 2. It should be like 150, right? If this is miles, that's 200. This is 100. So at 2 hours, she's 150 miles away, right? So I can find her slope I don't like writing a rock all the time, so I'll just call it M. Y2 minus y1 over x2 minus x1, which is 150 over 2, which is 75. And this is miles per hour. All right, your output over your input units. She's making pretty good time. She's not speeding too much. What about John? John started out in the suburbs. So his initial condition, he started 150 miles away. Okay, that's more than the suburbs, but you understand. And then at 2 hours, he's about 250 miles away. So his slope is going to be 250 minus 150 over 2 minus 0. So 100 over 2, so 50 miles per hour. He's cruising. He's probably on the phone talking. Oh wait, what was the question? Okay, so how fast are they traveling? So Mary's traveling 75 miles per hour. John's going 50 miles per hour. Who is faster? 75 miles per hour or 50 miles per hour? Mary, right? Mary's going faster. She's got that easy pass. She's on the expressway. And we can also tell this on the line on the graph, because see how Mary's line is a lot steeper? That's talking about like a greater slope. So 75 versus 50. So like this is a really, really, really fast, really, really slow. Is driving faster, we can see this because her graph is steeper. All right. So find the functions for their distance in Philly. We actually don't even look at the graph anymore, because for Mary's, we've already found her slope, 75. And what was her initial condition? It's 0. It's when x equals 0, it's the output for that. And we can see that right here, her initial, she started at 0. So that means that Mary's slope would be 75x. And John, we could do similarly. I already found a slope, it was 50. Right, because they have average rates of change or constant rates of change. So it's not going to change over different intervals. What was his initial condition? At noon, he was 150 miles away. So his was f of x of 50, 50x plus 150. And if you wanted to check to make sure these are right, check and see if you get these 2 points when you plug them in. Okay? So if I plug in 2 into this one, f of x equals 750, I'm going to get 150 out. Perfect. If I plug in 2 into here, I'll get 250, and that's what I want. Alrighty. So how far will they have traveled at 5 p.m.? So remember, oh, I don't want to be in orange, I want to be in maroon. So x equals 0 is noon, and x is, what's moo? Noon. So, and every x is an hour. So 5 p.m. is x equals 5. Alrighty. So for Mary, oopsies, you could have called it like m of x and j of x if you wanted to, but it doesn't really matter. So for Mary, f of 5 is going to be 75 times 5, which is going to be 375. Yeah. And I need to answer in units because we're given units. And John is going to be 50 times 5 plus 150. So 400 miles. Which is like pretty crazy, right? Is that it? Okay, done. So at 5 p.m., she's only 25 miles away from him, but they started at noon, 150 miles away from each other. So that's another example of Mary is getting really, really close to him, right? Is Mary ever going to take over and take the lead as a farther distance away than John? Yeah. She's going to be moving faster. So eventually she'll catch up to him, right? So probably in the next hour she will. And then we could talk about, I think in the next few sections, we talk about when they'll meet, right? So when they'll be at the exact same point. So that's pretty cool. Alrighty. So that's all about average rates of change, finding our initial condition, finding our slope between 2 points, putting them in together, and we got a function. Bada bing, bada boom. Pretty fun, right? All right. Your homework on this stuff isn't due until next Tuesday. So you have some time, but don't waste too much time. Okay. So I'll see you guys tomorrow. How do I stop recording? Oh, here it is.